So in 4.3, we do have the first derivative test for local extrema. And this reads, suppose that C is a critical point of a continuous function f, and that f is differentiable at every point in some interval containing C, except possibly at C itself. Moving across this interval from left to right, we have one of three cases here. If the derivative goes from negative to positive at C, then C is a local minimum. If the derivative goes from positive to negative at C, then there's a local maximum at C. And if the first derivative doesn't change sign, so it's either positive on both sides of C or negative on both sides of C, then there's no local extremum. One of the things that we should keep in mind is what it means to be a critical point. So that does mean that C is an interior point on this interval here, and either the derivative at C is 0 or the derivative at C is undefined. So we've got three cases here. So case one, derivative is negative before C and positive after. So if the derivative is negative before C, that means that it has to be decreasing. If it's positive after C, that means it has to be increasing. And since the function is continuous, it has to meet at that point. And we can see here that we have, if we go from a negative derivative to a positive derivative, that is indeed a local minimum. It's going to be a similar thing for case two, where the derivative is positive before C and negative after. If it's positive before, it has to be increasing. If it's negative after, it has to be decreasing. And since it is a continuous function, that does have to meet at the point C, f of C. Now, in these pictures, the derivative exists at C. I could just as easily go ahead and draw a case. We get something like that. Here, the derivative at C doesn't exist, but it's still a minimum. Here, the derivative at C does not exist, but it's still a maximum, or at least local maximum. Our third case here is that the derivative is positive on both sides of C, or the derivative is negative on both sides of C. And once you see one case, it's going to apply the same for both. So since it's continuous, there's f of C, And if it's increasing before, it comes in as such. If it's increasing after, it has to go out as such. We see something like this. On f of x equals x cubed, where x is equal to 0 there. We're going to get that derivative of 0 at x equals 0. But its derivative is going to be positive both before and after 0. And it would be the comparable thing for our third case there. Instead of an increasing function, we get a decreasing function. If you can picture negative x cubed, you'll get that same sort of twisty at 0 there. But either way, it's not an extremum at that point. It's because it's neither a maximum nor a minimum.